Hello, this is Dr. James Camp at Lee College in Baytown, Texas, and these are my comments on pointers in C++, which is Chapter 9 of Starting Out with C++ by Tony Gaddis. So far we have been dealing with variables in the idea of using a variable to store a value. And we've been storing those values in computer memory using only the variable name to identify where that is, and we haven't really cared about where in memory that variable was being stored. Each variable name is essentially an alias for a memory address. So if we write in the code int number equals 42, the system creates a variable called number, and it points to essentially an arbitrary memory address. Okay, in this case it's memory address 0004. Okay, memory addresses are expressed in hexadecimal usually, which is why after we get to 9 over here we go up to A. And so number points to 0004, and when we then set it to equal 42, the system puts 42 in that memory box. Okay, the identifier number is associated with memory address 0004, but we have no idea what address it is. We just know that that's where it's pointing to. So far in our programming experience, we've just used those variable identifiers. We haven't ever really known or really cared to know, or certainly not used, the memory addresses they refer to. But what if we want to know the memory address of a particular variable? C and C++ offer us an address operator, ampersand, to get the address of a variable. So if we type the code int num equals -99, then again we get a memory location somewhere in memory. Maybe this one is OC42, okay, and the computer stores -99 for us at that memory location and causes the identifier num to point to that memory location. Now, what if we wanted to know that 0C42, okay, that actual memory address? Well, we could use the ampersand operator and num, it's often pronounced, to retrieve not the value of num, but its address. So if we wrote on wrote in our C++ program cout insertion operator and num, okay, what we would see printed on the command line or on the terminal line would be OX0C42. OX. Okay. Remember, that's the code that indicates where the next number is in hexadecimal. Okay. So we can use that ampersand operator to get the address of a variable. We've seen the ampersand operator before, actually, when we wanted to pass a particular variable by reference in our C++ code. If we wanted to pass a reference to a variable to a function instead of just passing the value of that variable, we use the ampersand operator in the function definition. Now C, regular old C, doesn't have that, so you have to use pointers if you're going to try to pass values by reference in C. Okay, so let's look at this same situation we had before with number pointing to location 0004 and that location holding the number 42. If we created a variable called int pointer and we used the star operator to declare that this was a pointer, and we used the ampersand operator to indicate that we're storing the address of variable number in int pointer. No, I want to draw an arrow. Okay. Int pointer is created at a different arbitrary memory location. In this case, it's 0001, but it holds the address of number. So this variable can be said to point to number. Okay, its memory address points, or its value in memory points to this other memory address. We've already worked with something similar to pointers when we learned to pass arrays as arguments to functions. Okay, when we create an array int numbers bracket, square bracket, and maybe put 3 in here. Then we can pass numbers to the array, to the function show values. What we actually pass here is not a copy of the entire array. We pass a pointer to the first unit of the first value in numbers. And that's because of the way arrays are stored in C++ and C, which we'll get to in a minute. In C, if you store values as an array, it actually points, if you store value in numbers as an array, numbers actually holds an address that points to the first number in the array numbers. Okay, and if you then pass that to show values, the function, we're actually copying not the whole array, but this address is what's being passed. And when show values tries to access values at index count, it's going to look up this address and go, say we said values at 2, we'll go 0, 1, 2. Okay. We've also learned to work with something like pointers when we use reference variables. Okay. For example, if we wanted to get an order for a certain number of donuts, and instead of doing, standard C++ where this function would return the number of donuts, we wanted to just pass the number of donuts and have it return inside that variable. We had to pass that variable by reference. Okay, so we used the ampersand operator to get the to tell C++ that we're passing the address of Jelly Donuts down here, okay, not just the not copying the value of it. Okay. What happens here is Jelly Donuts is not a pointer, so it actually points directly to the Jelly Donuts variable here. But when we tell it we want to pass a reference, it's going to look up the address and pass the address over here instead of passing the value. So ampersand donuts down here is acting a little bit like a pointer. It's storing an address. Okay, so pointer variables are another way to work with memory addresses to work with a piece of data. They're more low level than arrays and reference variables, and the way you use them is a bit different. You have to use that star operator. And when you, unlike a reference variable, unlike a reference variable in a function or an array, you cannot assign a value, or you can assign a value directly to a pointer, but when you're doing that, you're assigning a memory location, not a, so if I created int star pointer, and then I said pointer equals 3, I'm assigning pointer to point to memory box. So we got 0001, 0002, 0003. It's pointing there. Whatever's in that memory location might be junk. Okay, there might be gobbledygook here. And so I would access that whenever I used my pointer, now that I've told it to point to location 3. So you are responsible for finding the address you want to store in the pointer and using it correctly. Okay, so this is how you use, and now that we've talked about some of the motivation for pointers, this is how you use them. You define an integer int star, and then the pointer name, we're calling it int pointer here. What this reads as to the computer as int pointer is going to hold the address of an int type variable. Where it's conventional to put the star just before the variable name, but really it can go anywhere in between. Some people like putting a space between the star and both words around it, int space, star space, int pointer. Some people like putting the star here attached to the word int and leaving the space here between, before int pointer. It doesn't matter as long as there's an asterisk character between the word int and the word and the variable name. C++ will understand you. Okay, how do we assign an address to a pointer variable? So let's say we have a variable named x, and we assign x equals 25. That means we're going to create an int type variable x. It's going to point to this memory location, and then we're going to stuff the value 25 into that memory location. But we currently don't know what the address of that is. The system does. The system knows that the address of x is 7E00. But we don't know that until we define a pointer. Okay, so I'm going to change colors here and make this a lighter blue. So pointer is defined here, and he points to this memory box, which is initially empty. We haven't initialized it yet. But then we use this statement, pointer equals ampersand x, and x. Okay, that takes the address of x, takes the, yeah, I can't draw ampersands. Anyway, takes the address of x and stores it in our pointer. And so now we could say cout pointer, and that would print this address right here. And now we'd know where x was being stored. That's not in itself a very useful thing unless you're a computer scientist who's really interested in how memory is being used in your program. But we'll see in a little while what you can, some of the things you can do with pointers that are a little bit more interesting. Okay. You can initialize pointer variables to point nowhere with a special system keyword called null pointer. In C++ 11, the null pointer keyword was added to represent the address 0. There is no address 0 in your program. It starts with memory one location past that, so this is a null pointer. It is pointing at nothing. Okay. This pointer, this program does very little. It stores it comes over here and stores 25, the value 25 in x. It creates pointer as a null pointer. Why is it doing this to me? Null pointer stores the value 0 in pointer. Okay. And then we let pointer equal ampersand x. So the address of x now gets stored in pointer. And so when we print out x, we print out the value of x, and then we print out the value of pointer, and we get 25. We get 25, and then we get the address of 25, the address of x. Okay. The star operator dereferences a pointer. So if we say int x if we say int x equals 25, we're storing 25. So we've got our memory here. 25 gets stored in, say, 4C 4.2. Okay. And x points here. Int star x pointer, okay, is now going to get the value ampersand x. So we create a new value here, call it x pointer, and it might be at location 20, maybe 1111. We'll go with that. And then it holds the value for C42 because ampersand x took that value and stored it there. Okay. Now, if we output x pointer, that's going to print the address of x. So that's going to print OX for C42. Okay. But if we prepend an asterisk in front of x pointer, if we print star x pointer, okay, that's going to dereference the pointer. So it's going to take x pointer, it's going to bounce off that value and it's going to end up pointing to 25. So that will actually print the value of x, which is 25. And if we type star x pointer equals 42, then we're going to take x pointer bounce off here till we get here, and we're going to change that value to 42. Okay, so that's how this star operator works. If we type x pointer, we're talking about the memory address. If we type star x pointer, we're talking about the value that it points to. Okay, this program uses that indirection operator to assign, we initially assign x to be 25, then we assign pointer to point to x, and then down here we change the value pointer points to from 25 to 100, and so it'll print out 25, 25, 100, 100. Okay. The relationship between arrays and pointers. This is where pointers really get interesting, is that pointers and arrays in C and C++ are essentially the same thing. In C and C++, an array variable is actually a pointer to the first element in the array. Okay, so if I type the line in C++, int vals, open bracket, equals curly 4711, okay, this works in C or C++, okay, it creates a variable vals which points to a random memory location and holds another memory location. It is, in other words, a pointer. And this pointer points to the starting address of the contiguous memory area that holds the numbers we stuffed into vals, okay, which is our 4, 7, 11 up here. So if we actually output vals, if we did cout vals and we didn't use the bracket operator, that would display the memory address that that vals points to. The square bracket operator looks up the value at the base address plus an offset indicated by the number in brackets. Okay, now ints in this system take up 4 bytes. So the first one is 4A00, the next one is 4A04, the next one is 4A08, okay? So if I call vals at 1, then I'm going to, that's essentially like using the star operator on a pointer, except it knows not just to look at this address, but to then add 1 to that and get my my second item in the array, which is 7. If you've ever wondered, or if you've been wondering for a while now, after we introduced arrays, why arrays are noted to start at 0 in C, C++, and a lot of other computer languages, this is why. Vals at 0 means don't add anything to the starting memory address, just look up this one right here. Vals at 1 says add 1 location to the memory address and look up this one. Okay, and that's why we can't ever call vals at n. If we set up a 3-point array, if we called vals at 3, we'd go here, 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 and we'd find that there's nothing there. Or rather, there might be something there. The computer might have stored something else in that memory address. We just don't know what that thing is because it's not part of the array vals. It's not what we expected to get. So an important thing to note here is that an array and a pointer are very similar. Vals points to a mem address. Vals bracket n points to value n plus 1. Okay, so vals at 0 points to value 1, vals at 10 points to value 11. Okay. Pointer val pointer points to a memory address. Star val pointer points to the value at memory address. Okay. So really the difference is which operator you use to dereference them. If you've declared it as an array, you can still use the star pointer to get the first value. If you've declared it as a pointer, you can still use the square bracket operator to get the next, to get the second value, the first value after where val pointer points. So really these things are basically interchangeable concepts. And that means you can do some cool stuff with pointers and arrays. You can do something like vals equals blah, okay. Val pointer, star val pointer equals vals. And then you can say val pointer plus equals 2. And now val pointer is pointing to value 11. Okay, so you can have two variables that are pointing to different, one that's pointing to the start of the array and one that's pointing to the end of the array, or halfway through the array, or whatever. So you can actually store the addresses of multiple parts of your array in different variables as long as you keep track of what you've done. Okay, and that idea is called pointer arithmetic. If we've done val pointer equals vals, then initially val pointer is pointing to this first value. What's val pointer plus 1? Well, val pointer plus 1, we're going to add 1 to this, and it now points to 7. Okay, so star parens val pointer plus 1 close paren is the same as the bracket operator 1. Star val pointer plus 2 is the same as the bracket operator 2. So why would you ever use this? I don't know. Maybe it works better for some reason. Where it comes in handy is that you can actually change the value of val pointer. You can say val pointer plus equals 1, and now it's permanently pointing at 7, and you now essentially have two variables, vals and val pointer, that are pointing to different parts of the array. Okay, this shows you that you can use an array with the square brackets. You can use a pointer with the square brackets. You can use an array with the star notation. You can use a pointer with the star notation, and it all gets you the same place in the array. So, in case you haven't figured this out by now, vals at I is how we pronounce that. Vals square bracket I is equivalent to star vals plus I. Okay. Note that there is no bounds checking performed in C++ or standard C, whether using an array name or a pointer. So if I declare an array of size 3, why is it doing that? And I put 0, 1, 2 in my array of size 3, and then somewhere else in the program I store the string x, y, z in a string that's pointing to the next set of memory boxes, and vals points here. Okay, vals square bracket 2 would get me this. Vals square bracket 4 would get me the value y, which of course it wouldn't return as y, it would return it as the numerical equivalent of that, because I told it I'm using an int. Okay, and that's what we mean by there's no bounds checking. In some languages like Java and C#, the compiler knows that vals stops at index 2, and vals 4 would do what we call throwing an exception. It would send a message back to the program saying, no, you can't do that, that's out of bounds. But in C++, in standard C and C++, this wall here I am trying to scribble and it will not let me scribble. Okay, that wall here does not exist. Okay, so instead, you can access an array you can go as far ahead as you want, even if that's not a valid operation anymore. Similarly, star vals gets me 0, star vals plus 2 gets me this variable, and star vals plus 4 gets me that. And that's perfectly legal. C++ will let me do it. C++ does not care that I'm accessing a different variable, or what was originally a different variable. It will let me pull that letter Y out of that array. It'll even let me say vals at 4 equals 32, and then whatever character number 32 is, that will replace this Y. And so I've now changed a string in my program somewhere. Okay. So this is a program that shows how you can use square bracket notation. All right, so I don't entirely pretend to understand the organization of Mr. Gaddis's slides here because we've talked about pointer arithmetic already, but here we are talking about it again. Really, the point here is that you can do more with pointers than just dereference them. Okay, we've looked at dereferencing a pointer here, but there's more that you can do with pointers. You can plus plus and minus minus them, which is the equivalent of moving one step forward or one step backward in an array. You can plus equal them, which is the equivalent of moving in steps forward in the array. You can also minus equal them, of course, to move that many steps backwards. And if you want to know how far you've moved in an array when you find a particular value, for example, you can do val pointer minus val. Okay, and this is the number of ints between val pointer and val. So an example of why you might want to do that is if you were searching through an array and you knew, you had 2, 3, 5, 7, 1, 9. You were looking for, so vals permanently points to the first one, even if you use the open bracket, the square bracket notation to get something else out of it, it still points to the first one. But if you use val pointer plus plus, then it points here check for 3. Let's say we're looking for number 7. Check here, sees 5. Check here, sees 7. Aha! We want to know what index we could see out 7 is at index val pointer minus vals. Okay, and that would say that val pointer is pointing to 3 beyond vals, so it would print out index 3, which would be correct. So that is a way to do array searches without having to have an extra variable that tracks the index, okay, that you're currently at. Okay, this one just uses num pointer plus plus to step through the array forward to print out the entire array, and then num pointer minus minus to step through the entire array backwards to print out the same array but backward. Okay. Initializing pointers, we've talked about initializing null pointers before, but you can initialize a pointer using the ampersand notation. So you can say int star num pointer equals and num, and that's going to make num pointer point to the memory location of num. You can also initialize using arrays, because as you know, an array name is really just a pointer. So you can say int star val pointer equals val, and that's going to make val pointer point to the same thing that val points to. One thing to note is that you can't mix data types with pointers. If int star pointer tries to point to double cost, that's not going to work because doubles are a different size than ints. Okay. We can compare pointers, and it's important to note that when you compare pointers, you're comparing the memory addresses. It's only when you use the star notation that you can compare their contents. So if we have an array of values 1, 3, 2, 4, 5, and pointer 1 points here and pointer 2 points there. Okay, the memory addresses are like 0, 0, 0, 1, 0, 0, 0, 5, 0, 0, 0, 9, because we go 4 units for each integer. So if we asked, well, certainly pointer 1 does not equal pointer 2, we know that. But if we did a greater than symbol here, okay, pointer 1 is 0, 0, 0, 5, pointer 2 is 0, 0, 0, 9, Address 5 is not greater than address 9, so that evaluates to false. But if we do star pointer 1, star pointer 2, star pointer 1 is the value 3, star pointer 2 is the value 2, 3 is greater than 2, so my God. So this expression evaluates to true. Okay, so we can also pass pointers as. So when you pass a pointer to a function, it works kind of like a reference variable, but it's a little more flexible because you can do pointer arithmetic with that pointer. You can plus it, you can minus equal it, you can then even return that memory address as the value for a new pointer. So if we say had a value here 32 and the it was a memory value, let's see, 0001, 0002, 0003. We'll just pretend that ints only take up 1 byte. And this is num here. And then we had a value pointer that hold 0003. Okay. And then okay, well that's not going to work because pointer is what they used for the. So let me. We'll call it num pointer. Okay, and then somebody declares this function void getNum int star pointer. Pointer is pointing to an int. Okay, but it doesn't. When we call that function, it creates pointer here. Okay, somewhere on the stack, and if we call that function as getNum and we pass num pointer, okay, then what gets copied to pointer is that 0003 value. And so now pointer points to the same value in memory that num pointer pointed to. And if we say cn star pointer, we're going to change the value of 32. But if 32 were part of an array, and there was also 21 and 43, then we could pointer plus plus, and it would now point here. And then we could pointer minus equals 2, and it would now point here. Okay, so that's why pointers are a little more useful, a little more flexible than reference variables when you pass them to a function. You can do all this pointer arithmetic with them. Also stands to note that while this is a C++ course, standard C does not allow passing by reference. It only allows passing pointers. So if you ever find yourself having to write a standard C program, as I am this semester in my operating systems class, if you want to pass something by value, you have to pass a pointer to it. Okay. So this is an example of how you can use passing by pointer. We call swap down here. We call and num1 and num2. Okay. So that will pass the address of num1 here and the address of num2 here.
Oh.
All right, this is a program, real simple program that shows that you can define functions get number with a pointer and double value with a pointer, and then you can pass the address of number to get number, and it will presumably get you the number, and then and number to double value, and it will, as you can see, multiply the value by 2. Okay. Now there are some odd little things here that I'm just going to pass over because they're not all that interesting. If you make a const int, you know that means that you can't ever change this value, right? But if you make a const double array, that means that each of these pay rates is also a constant and they can't be changed in the program. Well, the same idea works for pointers. You can have a const double star rates, which means that you now can't change the value that rates points to in this little program. In this function, it means that rates is constant. Okay. There's also the possibility of making a constant pointer, which means that the value is not constant, the pointer is. Okay, so if you do an int star const pointer, okay, get back to our little memory boxes here. So value points here, 22. And this is, say, memory address 0003, 0002, 0001. Pointer contains the value 0003. And because we made it a const pointer, it will always point to that box right there. It will never point to, you cannot say pointer plus plus or anything like that. That pointer is constant. But we can, in this case, value is not constant. So we can say star pointer equals 42, and this gets replaced with the value 42. It's not this value that's constant, it's the pointer that is. Okay. And of course, just to multiply ridiculousness, you can have a const int star const pointer, which means that both the value it's pointing to and the pointer itself are constant. Okay. Now we get to 55 minutes into the presentation. what makes pointers really, really cool, which is dynamic memory allocation. You can allocate storage, in backup. So far in our programming, we've allocated memory storage this way. Int num, or sometimes int num. Whoa. Scratch that. Int num equals 5, or double nums equals 1, 2, 3, 4. Okay. We've set particular amounts of memory aside at compile time. That means we have to know how much memory we're going to need when the program compiles. We have to know how many numbers are going to go in the array nums before we compile the program. What if we don't know? What if the person, is trying to enter a list of student grades and we don't know if that person has 24 students or 36 students? Well, we could get around it by always allocating an array that's too large. We could say int grades 100, and then as long as our teacher doesn't have more than 100 students, we're set. But A, that wastes memory, and B, we don't know that our teacher might not have more than 100 students. They might be trying to grade, might be a high school teacher who has 30 students in each of 6 periods, and then, wow, they're at 180 grades, right? So the point is, it would be handy if we had a way to allocate this memory dynamically, that is, allocate it while the program is running. And the way we can do that is using the new operator. This shows you how to use new to allocate a single pointer, okay, which is interesting, but not super interesting. We can allocate one new value at a time, but that's not a whole lot different than allocating values in the program, unless we're perhaps talking about a little more advanced topic like structured data, and we need to allocate the memory for a new student record that holds first name, last name, midterm grade, and final exam grade. And then, it's each time we allocate a new student record, we're allocating a chunk of memory. So maybe we don't want to just do student 1, student 2, student 3, student 4 at the beginning of the program. Still, this works best when you're dealing with arrays of things. And so this is where the new operator comes into its own as a really useful part of programming. If I don't know how many elements, let's say I'm doing finite element modeling on an airplane wing, and I don't know how many elements I want to split it into until the program runs. And then I say, how many elements? And the user inputs how many, and I can do this. Look, I can hit new, double how many, okay, and that allocates how many spaces. I didn't know how many there were at the beginning of the program, prior to this, we could only stick, if the way we've done it before, if we just say double double elements how many, this had to be a constant, okay, or an expression that could be evaluated as a constant at compile time. This is the new world that we get brought into by using the new parameter, is that we can use a number that isn't a constant to set the size of an array. Okay, and we can then use either square brackets or pointer arithmetic to access the array. We can say star array pointer at I, or star array pointer plus I. Either way works. Okay. The program will terminate, which the technical term for it is throwing an exception, if there is not enough memory available to allocate. So if you try to use the new operator and you've filled up your computer's memory, it will just throw an exception, which generally terminates your program. Okay. The opposite of new is the delete operator. You use delete to free dynamic memory once you've created a value. You have to delete it after you're done. And there's a delete with square brackets that works on an array pointer. It works on an array pointer. So there's a danger here with using dynamic memory called a memory leak. This was a big problem back in the days of C programming, before we had cool things like C++ vectors that managed their memory for us. And if you decide to use dynamic memory to allocate your arrays instead of using a C++ vector, you have to remember to delete that memory. So let's look at what would happen if you didn't. Imagine a loop that calculates statistics for a number of data points each time. The outer loop asks the user how many data points. Uses new to allocate an array for that many data points. So outer loop says how many, says new array of how many, then goes into an inner loop that cycles through all those, reads in and cycles through those data points. Okay, then we cycle back up, start the outer loop again, and we say another new how many. We never got rid of the old one, so the old one gets stacked up here in memory somewhere, and we've just created a new one. And then we run through that loop, and we come back around the outer loop again, and we create another new how many, and we just keep stacking up arrays in memory that we never clear the memory from. We never delete. Each time we start over at the top of the loop, we allocate a new array. Okay, so if we've done this 10 times, we now have 10 times, I don't know how many data points, 100. 10 times 100, that's 1,000 ints worth of data, or doubles worth of data, or whatever kind of data point we're storing. That can easily get into kilobytes or megabytes of wasted memory. And that means your program ends up leaking memory out of use that it no longer can get to and no longer can delete. And the program ends up taking up 10 times more memory than you ever meant it to. How to fix that? We just add one more step to our loop here. We add a delete command on the way up here that scratches out this data before we create this one. And this shows you that after we've created a new sales, we can delete it when we're done and free up that memory. Okay. Couple of other interesting notes here. You can return pointers from functions. So a function can return, instead of an int, it can return an int star. The function cannot return a pointer to a local variable in the function, however. Okay, remember that variable is on the stack and will go out of scope as soon as the function ends. It gets popped off the stack, it doesn't exist anymore. So your pointer would be pointing to something that isn't there. So to avoid that, the function should only return a pointer either to data that was passed to the function by reference. Okay, so you had an address to something outside the function to begin with, or to dynamically allocated memory. You can call new. You can have a function int star make array. Well, of int in, and then inside your function you say return new int of n. Okay, so you've just created some memory on the heap, not the stack, in the main part of the program, and that new memory will last outside the make array function. This get random numbers function creates a new int of num, a new int of size num. It populates that array with random numbers, and then it returns the pointer that we created. Okay, and I'm just going to click through this. This is kind of advanced C++ stuff. You can use special kinds of pointers that allocate their own memory and then deallocate their own memory when they're not being used anymore, as a way to avoid memory leaks. Okay. All right, that's it for pointers. I believe my next topic in this is characters and strings, and then we get to structured data, which is the last kind of fundamental topic in C++, before we get to the real fun of object-oriented programming.